Ductile materials such as most metals exhibit both elastic and plastic behavior. Wood is moderately ductile. Ductility is usually specified by the percent elongation to failure or by the percent reduction in the cross-sectional area. When a load is applied to a member, the deformations cause strain energy to be stored in the material. The strain energy per unit volume, or strain energy density, is equivalent to the area under the stress-strain curve. This area up to the yield point is called the modulus of resilience. The entire area under the stress-strain diagram is called the modulus of toughness. Shear stress and shear strain diagrams can also be established for a material. Within the elastic region, torque equal to G gamma, where G is the shear modulus found from the slope of the line. The value of nu can be obtained from the relationship that exists between G, E, and nu. Poisson ratio V is we call nu is a dimensionless material property that relates the lateral strain to the longitudinal strains. Its range of value is nu not less than or equal to 0 or not more than equal to 0.5.
The material for the 50 mm long specimen has the stress-strain diagram shown. If force 150 kN is applied and then released, determine the permanent elongation of the specimen. The formula of the elongation is elongation equal to strain in the plastic condition times length of the specimen. First, we have to find the stress. Stress equal to force over area. The force given is 150 kN over the area pi times 0.01 squared, and we get the stress is 477.46 megapascal. Since the normal stress is more than the yield stress, we cannot use the Hooke's law. Then we have to make the interpolation between the strain and the stress. So the strain, the normal strain is, find the strain at the plastic condition. First, strain at the plastic condition minus by the strain yield 0.00225 over strain plastic 0.03 minus strain yield 0.00225 equal to normal stress, which is 477.46 minus 450 over the stress plastic 500 minus 450, which strain equal to 0.017493. The formula for the strain at the plastic condition is strain minus strain recovery. Next, we have to find the strain recovery. To find strain recovery equal to stress over modulus elasticity. First, we have to find the modulus elasticity. The formula of the modulus is stress yield over strain yield, which equal to 450 megapascal over 0.00225, and we get the modulus is 200 gigapascal. As we get just now, modulus equal to 200 gigapascal. So the formula of the strain recovery is stress over modulus. The stress that we get just now is 477.46 over 200 gigapascal. So we get for the recovery strain is, so for the strain recovery is 0.002387 millimeter per millimeter. Next, we have to find the strain at the plastic condition, which strain at the plastic condition equal to strain minus strain recovery. Strain recovery that we get is 0.017493 minus 0.002387 equal to 0.01511 millimeter per millimeter. So just now, the formula for the elongation is strain at the plastic condition times length. So 0.01511 times by 50, the length of the specimen, then we get 0.755 millimeter.
Is an aluminium specimen shown has a diameter of D equals to 30 millimeters and a gauge length of L equals to 300 millimeters. If a force of 250 kilonewtons elongates the gauge length 1.50 millimeters, determine the modulus of elasticity, also determined by how much the force caused the diameter of the specimen to contract. Take the shear modulus of elasticity for aluminium is 26 gigapascals and the shear stress is 450 megapascal. This is the specimens, whereas this is the force and this is the length and the diameter of the specimen. The question asks us to find the modulus of elasticity. Given the diameter of the aluminium specimen is, from the data given, the value of elongation is 1.50 millimeters and the original length of the specimen is 300 millimeters. After calculating it, we get it 0.005 millimeters over millimeters. Since stress of since the normal stress is less than the yield stress, that is 450 megapascals, then the materials behave elastically. The modulus of elasticity is stress over strain. That is from the calculated that we have calculated 353.68 times 10 to the power of 6 pascal over 0.005. So we have calculated it, then we got 70.736 gigapascal. The next question is determine how much the force causes the diameter of the specimen to contract. Contraction of diameters First of all, we must determine the Poisson ratios for the material. By using the equation G equals to E over 2 times 1 plus nu, and the given shear modulus elasticity is 26 gigapascals equals to 70.736 gigapascal, we get the value of nu is 0.303. Since the strain longitudinal is 0.005 millimeters per millimeters, then by using the equation of nu equals to negative strain lateral over strain longitudinals, 0.303 equals to strain lateral over 0.005 millimeters per millimeters. Therefore, the strain laterals is negative 0.001802 millimeter over millimeters. The negative sign is included here since longitudinal elongation is positive strain, cause lateral contraction, negative strain, and vice versa. The contractions of diameter is therefore elongation. The contractions of diameter is therefore strain laterals times diameter of the specimens, 0.00180 times 30 millimeters. Then we get the contractions is 0.054 millimeters.